Good afternoon, everyone, in this conference. My name is Newton Mussolini. I'm a student of the graduate program in Applied Computing in Brazil at the Santa Catarina State University. I'm supervised by the professor Adriano Fioresi, and I will present the paper, A Comparison Between Traffic Classification Models for Bandwidth Management in Software-Defined Networks. So this is the agenda for this presentation. Well, the traditional internet is basically composed of interconnected autonomous systems that generally do not implement solutions that take into account the needs of the applications. So we say they deliver data with best effort only. On the other hand, applications are designed to work with some minimum network requirements, such as a certain amount of bandwidth, a maximum packet loss, and a maximum delay, that we call the quality of service of the network. To change this landscape, new network architectures have emerged, such as the software-defined networking that moves the network control from the forwarding devices into a new device called the controller. This way, the controller can program the network dynamically. The FlowPre-SDN is a framework for the RU controller that provides quality of service to data flows using a combination of QoS with OpenFlow meter rules and internal network state management. So the QoS rules that the FlowPre-SDN configures only handle packets from the same flow that have inter-arrival time of less than 10 seconds, that we call a subflow. And the FlowPre-SDN doesn't identify the flows by itself. So we intend to implement machine learning models to identify patterns of data traffic and classifying them into classes of services in real time. Therefore, our goals in this work are to provide a comparison between machine learning models that use batch data and those that use streaming data, as packets of application flows can be used both ways. And also, we'd like to identify the influence of the number of packets used for the classification. So the first thing that we had to do was to find a database of packet captures of common applications that represents the type of traffic that the controller would have to face in an applied scenario. We found the ISCX VPN and non-VPN databases from 2016 that are very diverse in terms of application types. They have packet captures of Vibebuster, YouTube, Netflix, Hangouts, and some other applications. Then we grouped these applications in classes of service based on the nature of the application to reduce the amount of classes for the classification. And we did a search on the application websites to find out their specifications in terms of bandwidth utilization. When some applications didn't publish their requirements, we got the values from other data traffic studies in the literature. Then we defined the label for the applications to be used in the classification as the class of service name and the highest bandwidth of the class that we found. After that, we have to adjust the database according to the way subflows of the SDN scenario looks like. So we use the Python library named Scapy to extract the data flows of the capture files of each application into individual files. Next, we removed some data flows that are not interesting and could be identified by the port number in the controller, such as the DNS, LMNS, and ARP. After that, we take the flow files that we generated to extract the subflows into individual files. And then from the subflows files, we will extract the samples to calculate the statistical information to use in the classification models. So here we have the selected features chosen to represent the statistics of the samples. We basically have information about the protocol number, if it's a UDP or TCP flow, the duration of the sample, the time between the first and the last packet of the sample, some information about the size of the packets, information about the inter-arrival time between packets, and the TCP flags that they use. So we defined two scenarios to analyze the influence of the number of packets on classification. In the first scenario, we divide the subflows into samples of 10 packets each, and in the second scenario, into samples of 30 packets each. This way, we had to generate 4 data sets, two for the batch-based models and 2 for the streaming-based models. And we also had to balance those data sets. So the main difference in terms of data between those two types of machine learning models are that for the batch models, each sample is processed into a set of features which will lead to a classification, whereas for the streaming models, each packet in the sample generates a set of features which we calculate the average by 2 by 2 that will lead to a classification. So in the streaming models, each packet generates a set of features that generates a classification. So to evaluate these scenarios, we selected some state-of-the-art machine learning models to compare. For the batch-based models, we choose the decision tree, which is a single tree that does the classification. The random forest, which consists of a set of decision trees. The support vector machine, that is a mathematical model and is also very explored in the literature. And for the streaming-based models, we choose the Hofting adaptive tree, which is a modification of the decision trees for the streaming, and the adaptive random forest, which is basically a group of Hofting trees. So to test and train these models, we use the k-fold cross-validation strategy. We choose k as 5. Thus, we separate the data set into 5 parts and iterate 5 times training and testing, where in each iteration, one part is prepared for testing and the other for training. And one detail that we choose in this part was to limit the streaming-based models to have not more than 20 flows feeding it at the same time, because we had bad results in previous tests. And the computer used for these experiments was an AMD Ryzen 5 with 20 gigabytes of RAM running an Arca Linux operation system. So after the cross-validation iterations, we obtained these results. For the scenario of samples with 10 packets, we have the random forest and the decision tree models with the best performance, with very low standard deviation, while the streaming-based models didn't have very good results. The decision tree got 97% of precision, the random forest 98%, the SVM 90%, while the Hofting adaptive tree 75%, and the adaptive random forest only 88% of precision. In the scenario with samples of 30 packets, we noticed that the random forest and the decision tree still performed the best, whereas the streaming models showed some improvements, implying that the number of packets in the samples is of the great importance for those models. The random forest still got the highest precision, 98%, but the Hofting adaptive tree and the adaptive random forest both got 91% of precision. Therefore, in this article, we presented a comparison between machine learning models that are based on different data structures, the batch-based and the streaming-based. We processed the data set to look like what the Flow-Pre-SDN would face in this SDN scenario. We choose some state-of-the-art machine learning models to compare, and as the result shows, the random forest achieved the best performance even using only 10 packets. However, in this work we didn't fine-tune the models, so the results may vary, but in general they were good. Right? And as this is a work in progress, we have defined some future works So we want to add some other classes to represent different applications and also different levels of quality of service requirements. Then we want to implement these models in the Flow PSTN and carry out some simulation tests to better understand the influence of the classification models in scalability. So this was my presentation. Thank you. And any questions?